We started section 2.1 last time. We were taking a look at finding derivatives with this limit process with the definition of derivative. This is one of the definitions of derivative, the one that has the notation f prime of x. And we had done two examples. The example we had done over here looked like a polynomial, right? We had done this example here that is a rational function. And our third example that we're going to do is going to be a radical function. So I chose three distinctly different types of examples so you can see them. But I also want you to notice that they have slightly different directions. Example number one, at the very end we had to plug in an ordered pair point, at least the x value for it, to find the slope at that value, right? Example number two left it sort of the most ambiguous, right? There's no plugging things in at the end. This is not the function itself, but this question is the least amount of work question, okay? Just saying find the derivative, okay? And then the one that we're going to do next is going to actually have us find an equation of a tangent line. This is the most involved of the three because there's an additional step at the end that we haven't yet done. All right, so we learned last time something called the four-step method. I talked about the fact that if you don't like it and you want to use the other one, that's okay with me. But I'm going to use the four-step method. Now our directions here on part A say to find an equation of the tangent line. Okay, tangent line red flags you, or it should. Tangent line means that we're looking for a derivative, and then we're going to do something with it next. Okay. Part B says to use a graphing utility to verify. So I'll show you how you do that as well. So part A involves three things. The first thing that we need to do is that we need to find f prime of x. The second thing we're going to do down here later, so this is like step one, we're going to have to find this. You know what? Let me write it over here to the side. I'll just write it like this. Step one is to do this. The next thing we're going to do is we're going to evaluate it at the point that we were given. The x value is actually an x value of 1, so we're going to find the value at f prime of 1. And then we're going to find a line. And the equation of a line that's helpful for us right now, it's not the only one you could use, but one of them that's helpful, is the point-slope form of a line. Okay, so y minus y1 equals m times x minus x1. Does that look familiar? So these are the three pieces that we're going to have to accomplish in this problem for part A. Part B is just looking at a calculator, so it's not really an involved question, okay? Part A is where we're going to do all the work. So to start with this, we first need to find the derivative, and we have a limit definition in section 1, right, 2.1, that we've been using and we will continue to use. The limit as h goes to 0 of f of x plus h minus f of x over h. So if you want to do it all in one fell swoop, you can. I'm going to do it in pieces. So I'm going to do the limit, or the steps, the four-step method. So I'm going to do step 1, and step 1 is finding f of x plus h. Okay, so f of x plus h means finding my equation. Yep, Levi? Nope, I don't care which one you use at all. I'll have answer keys written up for both, so whichever one you use, I'll know how to do partial credit. The partial credits don't mimic each other perfectly because the steps are slightly different as you go, but yeah, it's not a problem for me. All right, so we're going to take f of x, which is the square root of x, and we're going to replace the x with x plus h. So this step on this one is easy. There's no simplification. I don't have to square anything. I don't need to rationalize anything. There's nothing to do. It's really straightforward. So step 2 is to take that f of x plus h and subtract f of x. This is also an easy step for this particular function. So the step 1 is first, and then I subtract the original equation that I was given, square root of x. Again, I don't have to simplify anything. I don't have to do anything else. This is just step 2. Step 3 is the one where I'm supposed to divide by h. So I'm going to take the step 2 that I just found, f of x plus h minus f of x, and I'm going to divide by h. Okay, now if I were to just move on to step number 3 here and try to put 0 in for h, I'd have a problem, correct? What would happen to this fraction? If I try to put 0 in for h, what happens to this fraction?
0 in the denominator.
0 in the denominator, but not just 0 in the denominator, but also 0 in the numerator, right? So we talked about this back in chapter 1. When we end up with a 0 over 0, that means there's something I need to be able to do. I might need to rationalize something. That's going to happen on this one. I might need to factor something. We saw that happen with more polynomial type ones. Or I might need some trig simplification. I don't have trig on this one, right? Those are the 3 different methods we have. So because I see radicals here, this one's going to be a rationalizing problem, okay? And the way we rationalize is that we take wherever the radicals are, in this case it's our numerator, and we multiply by the conjugate. So I need to multiply by the square root of x plus h, and then since I have subtraction here, right, I'm going to do addition over here, plus the square root of x. And if I do it on the numerator, I also have to do it to the denominator. The numerator is the part that cleans up. I mean, that's the reason we chose what we chose, is because it will eliminate the radicals. Because these are conjugates, the inner and the outer terms, if multiplied, are going to match and cancel one another out because their signs are different. So I actually will only end up with the first 2 pieces being multiplied, which will eliminate the radical and give me just x plus h. And then I have a negative times a positive, so I have subtraction. Then I have the square root of x times the square root of x, which is x. So no more radicals in the numerator if I've used the conjugate properly. The denominator, I don't want to actually distribute. We don't want to make it messier, and that will actually make it messier. We want to leave it as is. Okay? So I know it doesn't look very pretty, but that's okay. The numerator will clean up a little bit. How will my numerator clean up? Yeah, it'll clean up and give me just an h, right? So the x here and the x here cancel. I'm left with just h. And lo and behold, there's that h on the denominator that I didn't distribute through on purpose. And I'm able to do what?
Cancel out.
Yeah, I'm able to divide those out. Yes, and that will always happen. That h should divide out if I've done all the other pieces okay. So this leaves me with what sort of feels like it's not any better. Right? It looks like it's an awful lot like what we started with, but it is better. And it's better because I'm actually able at this point to put 0 in for h without causing the 0 over 0 problem we had before. So this is the end of step 3. It's the simplified, cleaned up part of it. Step 4 then is to take the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. Okay, so if I put 0 in now for h, what will I get? Sorry, let me move this up. I'm trying to shift for the moment, so I'm not. There we go. So if I put 0 in for h, what am I going to get? So 1 over what? Yep, square root of x and square root of x. Or some of you are already telling me it's 2 square root of x. Okay? So there's no need to rationalize this denominator for a couple of reasons. The first reason is because depending on what x is, this might already be a rational number. Right? What if x is 4? I don't need to do any radicals in the numerator. It doesn't matter. So the arbitrariness of what x is means there's no need to rationalize this ever. Rationalizing something when we're at the end of a problem has to do with taking something we know is irrational, like square root of 2, and not leaving it in the denominator. We don't know what square root of x is. We don't know if it's rational or irrational, so we don't have to do that, period. The second reason why we wouldn't want to do it here is because that's not the end of the problem at this point anyway. Our question did not ask us to find the derivative, although we just found it, right? This is f prime of x. It is 1 over 2 square root of x. But we weren't asked to do that. Like the directions on this one asked us to do that and we would be done, correct? But we're actually here asked to find a tangent line. So I wrote out these 3 steps side by side, and we've done step 1. We have found f prime of x. The next thing we need to do is we need to figure out what that value is at this particular point 1, 1. Okay? So we find f prime of 1. So over here, we're now going to find f prime of 1. So if I put the number 1 in here, what do I get? It's very nice. 1/2. You bet. This is just a number 1/2. Yeah? Now, if at this point we had gotten a radical 2 in the denominator or something like that, we would need to rationalize it. So let me just say that real quick. This point, we would actually have numbers where they need to be, and we might have to do some rationalization. On this one, of course, we don't. It's just 1/2. Okay, so the third thing then is to find y minus y1 equals m times x minus x1. Does anybody know what this 1/2 is in that equation? Slope. It's slope. What's the letter for slope in my equation? M. Yeah. We found slope. Okay, so finding a derivative is finding a slope. This 1/2 will go right here. What else do we know in this equation in the problem already? Like, what were we given? We were given what? The points. We were given the point, in particular 1, 1, right here. What do I do with it? Yeah, Sophie's right. So we're going to put it into y1 and x1. So over here, I've got y1 and x1 are each 1. And the pieces I don't know, of course, are x and y. Let's see if I have another screen. I do. All right, let's actually take this to my next screen so that I have more space. So we're going to simplify our equation that we just found and put it into y equals format, in part because it simplifies and cleans it up, but also in part because on part B, it wants us to graph something, so it's easier to see it that way. So we're going to, I don't know why that says equals. Sorry about that. That should say minus. There we go. So we're going to distribute the 1/2. So 1/2 x minus 1/2. Then what we do? Add a 1. Yeah. Add my 1. So y equals 1/2 x what? Plus 1/2. Decimals, fractions, I don't care. If you do have something that's like a repeating decimal, you're going to want to use fractions, so don't write down 0.3 repeating. But for this one, decimals and fractions are equivalent. They're fine. So if you prefer decimals, go for it. All right, so this is part A. This is the end of part A. So we need to do part B. Part B is going to involve us graphing this thing, okay? So go ahead and grab your calculator. There are 2 equations we're going to put into the calculator are the original equation we were given, which was f of x, equals square root of x. And so this one we'll put in as y1. And then y2 we'll put in the equation we just found, 1/2 x plus 1/2. Okay, those are the 2 equations we're going to put in. Okay, so I put it in decimal form because it's quicker to enter. So these are my 2 equations. We're going to graph it, and we're caring about the point 1, 1, right? It's nearby the point 1, 1 that we care what happens. So I'm going to make my window a little tighter than I normally would. I'm just going to go from -5 to 5 and -5 to 5 here. because I want it to be just a little bit tighter of a window, and I'm going to graph it. So there's that square root function, and then there's my line. And you can see right here is 1, 1. And we could zoom in if you want to do so further, but you can see that tangency happening, right? I am going to zoom in a little bit. When you use the zoom in feature, you've got, it tells you 0, 0 here at the bottom, and you can't hardly see it, but there's a blinking cursor right there in the middle of where I've got going on. So I'm going to go over here to closer to the point 1, 1. It doesn't have to be exact, but nearby it to zoom in. And you can see it doing it, right? It's bouncing off of the curve exactly like we're going to expect. So why does this matter? Well, it's definitely a good check step to know, did I make a mistake? Right? If you had inadvertently entered a -1/2, say right here, and you graphed it, it wouldn't make any sense. Right? This graph doesn't make sense. You know there's a problem. You've made an error either in finding the derivative or in evaluating it or in simplifying for the equation. It's time to go back and look at the edit what you've done and figure out what the problem is. So our graph, if I zoomed in, right, looked like this roughly, with a tangent line that I'll change colors, that looked basically like that. Okay, so my dimensions are not, it's not to scale, but it's something like this. This is the graph that shows up. Okay. All right, just a couple more things in section 2.1 before we're done. There are some places where tangents don't exist. Tangent lines in particular do not exist when there's discontinuities, sharp turns, and vertical tangent lines. So discontinuities include a couple of things, 3 actually. They include holes, jumps, and asymptotes. So, visually speaking, right, a hole looks like this with a little spot here that's not existing, right? There's a hole. If you have a jump in the graph, you may have something like this, and then it comes up here, and then it does something else. It's a jump in the graph. And then, of course, asymptotes come from rational functions, so they might look something like this. So right here in the middle, like that, you have an asymptote that doesn't have one. Okay, so discontinuities. Those we might have expected because we kind of talked about those. We've talked about those a lot, actually, when we did continuity in section 1.5. We haven't talked about sharp turns. So sharp turns look something like this. I don't need there to be a dot there. Let me try that again. There we go. So if the direction changes sharply, and it doesn't even have to be this sharp, by the way. If it changes even like this, right? Any of these corners, or sometimes we call them cusps, that happen, the derivative won't exist there. And there's a very good reason for why. So if you think about tangent lines, as we've been discussing them, and drawing these tangent lines here as you get closer, what ends up happening is that once you move beyond that corner, the tangent line drastically changes, right? The limit from one side does not approach the same as the limit from the other side. The two limits are drastically different. Right? We switch on a dime, right? We switch what their limit values are. That's why it doesn't exist. The last one will come up in one of our examples at some point. I don't remember where exactly it is, but it's very uncommon, but you should be aware that it can happen. If you have a curve that looks something like this, and you were finding tangent lines, this particular point right here, I didn't mean to draw it dotted. If I found a tangent line right here, try to draw it. Okay, that should look vertical. Pretend like what it is. This is a vertical tangent line. Okay? So there's nothing wrong per se with a vertical tangent line, except that, do you remember what the slope of a vertical line is? Undefined. The slope of a vertical line is an undefined value. So if it's undefined, that means this whole limiting process can't give me a number, because it's undefined. right? So the value itself or the slope itself does not exist, is another way to say that. It's not that the tangent line doesn't exist, but the slope doesn't. So the slope, which is what we're talking about when we talk about a derivative, would not exist in that case. So let me actually show you an example. Oh, sorry, I have one theorem, and then I'm going to show you an example of one of these things happening, and I'll show you how to use your calculator to see it. All right, if you have a differentiable function, it is automatically continuous. Notice it doesn't say if and only if. In other words, just having a continuous function does not necessarily make it differentiable. And cases 2 and 3 over here showed you examples. 2 and 3 were continuous. But one has this sharp turn, and the other one has this vertical tangent line. So continuity does not guarantee that you have differentiability. But if it's differentiable, that means has a derivative, it is continuous. So if you know something has a derivative, it's continuous. All right, so this is a fun example. We're going to do it with your calculator to see how it works. So if you flip over to your calculator with me, I'm going to show you how to put this in. So clear out what we did a moment ago. So our example says that we have the absolute value of x squared minus 9. So if you hit the math button, and you arrow over one time to the num menu, you see it says ABS. I'm not sure if all of yours say ABS. It might also show symbols that look like absolute value symbols. But go ahead and select that symbol, number 1. If you have the older operating system like mine, it actually will type in ABS with a parenthesis. If you have a newer operation system, it's going to put in absolute value symbols for you, which is better, but it's okay. Either way, we're going to type in x squared minus 9 next. So yours either looks like this, where I have ABS and I've got the parentheses around it, or it actually put in absolute values and you actually have the x squared minus 9. Okay? Because we don't have necessarily any go-to, what should I graph this in? Let's just hit zoom 6. 6 is our standard 10 to negative 10 on both axes windows, so I'm going to choose that one for the moment. You're going to see a kind of interesting graph. Okay, so what literally you're seeing here is you're seeing an absolute value graph. Oh, I didn't mean to grab that. Man, I'm telling you what, I meant to grab my iPad there. Okay, so what you're seeing here is you're seeing an x squared graph. Like if this thing had been x squared, it would flip down here. But when you have absolute values, it takes everything negative and makes it positive. So the bottom part of this parabola gets flipped up. Can you see that? That's what's happening. The bottom part of the parabola gets flipped up. Cool, right? So this part right here that looks almost like you've got kind of like a W graph has these corners down here that are very sharp turns. So these sharp turns are going to cause problems. We're not going to have derivatives at those corners where that's happening. Can you tell either from the picture or from the equation where those corners are happening? What x values? 3 and negative 3. Now, from the equation perspective, right here, why should it be 3 and negative 3? Because that's where it becomes 0, right? Between 3 and negative 3, imagine putting in the number 2 here. If I put in the number 2, what's going to happen inside my absolute value? It's going to get negative 5. It's in the part that's been flipped up, correct? Right, so what we have here is we have a graph that looks something like this. Whoop. So over here at 3 and over here at 3, so negative 3 and 3, we have these parts of the parabola, and then it flips up right here. And the question asks, where is it differentiable? Well, it's mostly differentiable everywhere. It's definitely continuous. I don't have any weird vertical tangent lines. I just have these corners or sharp turns or cusps where it's not going to work. So if I want to talk about where this is where this is differentiable, I would go from negative infinity to negative 3. And I wouldn't include the negative 3, right? It doesn't work at negative 3. So I have parentheses on those. I'll put a union. Union means it's joining it to the next piece. And then I start back up right after it doesn't work, it works again.
3.
From -3 to 3. And another union from 3 to infinity. And it's differentiable in all those places.